So let's do an example here. Let's say that we've got a region of magnetic field. So we got a magnetic field here, and let's say the magnetic field has a magnitude of 0.00849 Tesla. So in other words, that's going to be 8.49 millitesla. And I'm going to shoot a beam of electrons in there, and my electrons have an energy of 1.45 kiloelectron volts, so 1.45 keV. Okay, and so how would I do that? Well, what I would do is, that's really straightforward. To get that beam of electrons, I would really just have to have a negative plate and a positive plate here, and I heat the negative plate, the electrons come loose, they go shooting off that way. I just got to make sure the voltage between the two is 1.45 kilovolts. And so the electron's going to come through because it's got charge E, then it's going to be kilo electron volts. So what's going to happen? Well, right-hand rule, V is this way, magnetic field in, so right-hand rule says up, but they're negative, so they go down. So they're going to spiral this way. So they'll be spiraling around clockwise. And so I want to know what is the radius here of the cyclotron radius and what is the cyclotron frequency for 1.45 kiloelectron volt beam of electrons. So, well, this is pretty straightforward. It's like pretty much plug and chug that R equals mV over QB, and the frequency is just going to be QB over 2 pi m. Now, the only difficulty is, what's V? Well, that's not voltage, that is velocity right there. So I need to know the velocity of a beam of electrons that has an energy of 1.45 keV. Okay, well, I know that this is a measure of energy. Electron volt is a measure of energy. So I know from way back in one of the first chapters we did this semester, an EV is 1.602 times 10 to the minus 19 joules. So a keV is going to be 1.602 times 10 to the minus 16 joules. So 1,000 times more. So that means that 1.45 keV, if you do the unit conversion, that's going to be 2.32 times 10 to the minus 16 joules. Well, that's nice. I found the energy. Well, I know that energy is kinetic energy. Kinetic energy is 1/2 mv squared. So V is going to be the square root 2k over m. So that'll be the square root of 2 times 2.32 times 10 to the minus 16 joules divided by the mass, 9.11 times 10 to the minus 31 kilograms. So the velocity is 2.26 times 10 to the 7 meters per second. So in other words, just a little bit less than 10% of the speed of light. Okay, so these are pretty fast electrons here. And so the electrons, now we're ready to find, the cyclotron radius, mv over qb. So the cyclotron radius is 9.11 times 10 to the minus 31 kilograms times this velocity we just calculated, 2.26 times 10 to the 7 meters per second. Okay, divide by 1.602 times 10 to the minus 19 coulombs. And the B, I said, was 0.00849 Tesla. So the cyclotron radius is going to be 0.0151 meters. Okay, so about 1.5 centimeters. So that means that the entire orbit here is going to be about 3.02 centimeters. So that means that you would have to have a clear opening that's just a little over 3 centimeters around, and the thing would be able to circulate in there. Okay, well, that's not hard to do. Okay, what about frequency? The frequency is QB divided by 2 pi m. Well, we don't need anything other than just the basic stuff here that we have. 1.602 times 10 to the minus 19 coulombs. That's going to be the charge of the electron. Again, we'll take absolute value of this because there is no such thing as negative radius or negative frequency. And then the B, which is going to be 0.00849 Tesla divided by 2 pi times 9.11 times 10 to the minus 31 kilograms. So the frequency turns out to be 2.38 times 10 to the 8th hertz, or in other words, that's 238 megahertz. Okay, so what have we done? We have fairly easily accelerated electrons, squirted them into a magnetic field. They're spiraling in a cavity. Now, one thing that's happening is that as they're moving, one of the things we're going to discover is that moving electric charges make a magnetic field. They move one way, move back the other way, so the magnetic field keeps oscillating. They keep changing distance, so the electric field keeps changing, and they make changing electric and magnetic fields, basically electromagnetic radiation. Electromagnetic radiation with a frequency of 238 megahertz. Now, that is in the UHF part of the spectrum. Now, the thing, though, is about 238 megahertz, that radiation, if it hits something out here that's made of metal, it's going to bounce back. Okay. And so this was something that they did in World War II, was they figured out a way of making a little miniature particle accelerator that could accelerate these electrons. You know, all they had to have was about 1.45 keV or kilovolts, and that's not that hard to do. And so electrons are real easy to accelerate. And then you had to have a little empty cavity in a vacuum that was, you know, a little bit more than 3 centimeters across. And that's pretty easy to do. That's a little more than 1.5 inches across. It's perfectly going to be fine for you to do that. Okay, and so you inject it in there and it spins. And what happens is, as it's spinning around here in this magnetic field, it's producing these radio waves, and the radio waves can go and bounce off of something. And so if you were able to measure the time it takes there to get back, and we'll talk about how you do that later, then that would give you a range of the thing it's bouncing off of. And so by telling what direction it comes back, you can then use this radio detection and ranging equipment to be able to detect metal things like enemy aircraft or submarine periscopes or warships. And so radar became a tool during World War II. And this is basically how they did radar in those days.